This is the 5th Agromatics live webinar. ISAM President Professor Lipping is together with us. Professor Lipping, would you like to tell something before we start?
Okay, yeah, welcome everyone. Today we invite Professor Jenny Liu to give us a talk, and Jenny is well known in the hyperspectral remote sensing area, and so we welcome Jenny to join. And maybe Bert, you can introduce more about Jenny.
Okay, sure. Hello again. As you know, my name is Berk Üstündü. I am the Vice President of International Society of Agromatics, and this is the 5th session of Agromatics webinars. And today's webinar is entitled as Hyperspectral Image Classification and its Agricultural Application. First of all, as always, I again suggest non-ISAM members participate to be registered to ISAM through www.agromatics.org so that they can be informed about activities of the Agromatics community and take ISAM's other future benefits. Now, please keep your microphones muted, and you may ask questions anytime by utilizing the chat function, or you may ask also by the end of the session, and all of them will be answered by the end of the session. And you know, hyperspectral imaging is rapidly gaining significance in agricultural applications due to its transformative capabilities in crop management and precision agriculture. And processing methods of wide range of spectral data is a key factor for the performance of hyperspectral imaging-based applications. And here in this webinar today, Jenny will present recent data processing models and machine learning methods for hyperspectral image classification. And Jenny is a Bobby Sheckhouse professor in the Department of Electrical and Computer Engineering at Mississippi State University in the United States. And she is a world-renowned researcher in hyperspectral remote sensing image processing analysis. And as most of you know, she is the fellow of IEEE and International Society for Optics and Photonics. And she will become the new editor-in-chief for the SPI Journal of Applied Remote Sensing starting by January 2024. And she was previously the chief editor-in-chief for the IEEE Journal of Selected Topics in Applied Earth Observations and Remote Sensing, known as JSTARS. And she was named to the Clarivate's list of highly cited researchers in 2021 and 2022. And in addition to hyperspectral imaging, her research interests also include its applications in agriculture, forestry, wetland, and water quality monitoring. And you're all please welcome. And I would like to pass now to the presentation by Jenny. Jenny, you are welcome again.
Thanks for the introduction. Today I'm going to focus on the hyperspectral image classification and using representation-based approaches. So here's my outline for the talk. I will briefly give the background on the hyperspectral remote sensing, then introduce the classification approaches, then give some examples on tillage practice mapping. Then we'll discuss experiments and draw some conclusions. So here's some background information: multispectral versus hyperspectral. I think most of us already know that hyperspectral sensor can acquire images in many very narrow spectrum bands. So that means the sensors doing very dense sampling in the spectral domain. Because of that, the resulting image has very high spectral resolution. So the data we often used, it has like a 10 nanometer spectral resolution. Sometimes we can get the data with 5 nanometer or 3 nanometer spectral resolution. Because of that, this data can help us to achieve very accurate material identification, in particular if those materials have pretty similar spectral response. Compared to the traditional multispectral sensors, which acquire images in several broadbands, that is the advantage of hyperspectral sensing. However, multispectral sensors usually have relatively higher spatial resolution. So this spectral and spatial resolutions are some kind of trade-off. So for agriculture application, I believe if we want to do precision farming, then the spatial resolution could also be very important. So in such applications, we probably need to do like a hyperspectral and a multispectral data fusion, but that's not my topic for today. So this is just some illustration for the average data we're going to use today. You can see that for different materials, it has a different spectral signatures. So based on that, we can do a better or much finer classification. So this is also show the advantages for HSI. For the same area about the forestry, using the hyperspectral image, we can do very detailed classification for tree species. But if we use the multispectral image, we can only do very broad classification. So if the materials or classes, they already have very different spectral signatures, we don't really need hyperspectral imaging. But if we want to do, the species separation, then the hyperspectral image really can provide the advantage. So there are some challenges in HSI image processing. Like spectral variability, I believe that is for all the remote sensing data. So because the signature in the library or the signature taken by the sensors, they could be different. So directly using those deterministic approach for comparison may not be able to offer good performance. So we have to consider this variation by using some statistical approach. And then for the mixed pixel, this is the one just mentioned for hyperspectral images. Its spatial resolution is not that high. So the areas covered by a single pixel may have different type of materials. So the signatures are often mixed signatures. So because of that, a mixing analysis is also a very important topic in our area. And certainly, hyperspectral has very high data volume. In spectral domain, it has high redundancy. So how to deal with this high data volume, particularly when we have very limited training sample, that could be a big issue. So we have a research topic, which is dimensionality reduction and the feature extraction. So the objective is we want to reduce the data or we want to trim the data, but meanwhile, we want to find these very useful features for various purposes. So that could be many different ways we can do this. We can do band selection, or we can do, projection. I mean, just this one topic, we can do many different things. And the spectral mixing, I just mentioned that, right? We can do linear mixing, we can do nonlinear mixing. Nowadays, we also do use like a deep learning, we can do unmixing. For unmixing, we can also assume the end members are pre-known, or we need to estimate this end member. So there are also many things going on in spectral unmixing. So today I'm going to focus on classification. We know that classification is to assign a label to a pixel. So in our case, we assign labels to each pixel. We're not doing like object classification or scene classification. So the classification is pixel based, and then it could be supervised if we have the training sample, or we can do unsupervised if we do not assume we have a training sample, or we can do semi-supervised. We have very limited amount of training samples, and we also want to use unlabeled data and so on. Then there are many things in this topic. Then for target detection, this is to detect those very small amount of pixels to say if they are belong target or they belong to background. So in this case, we do not assume we have training samples like background, or we have training samples for target. We merely just assume we have a target signature, either spectral signature or spatial template. And then this could also be supervised or unsupervised. If it is unsupervised, that means we don't even know what is target. We're just looking for something very different from the background. So target detection, anomaly detection, there's also have very important applications. Like in agriculture, if we want to detect the early crop stress, but we don't really know how the signature become. In this situation, we probably can apply some anomaly detection approach. So this is also something very interesting. And then for chain detection, this is I believe that is a very early application of remote sensing. It is to find the significant changes between two data from the same sensor or from different sensors. And the changes could be, it's not a background or like a seasonal change, right? We want to know the changes that is of our interest. Most likely that should be dynamic change. And also I mentioned like we can do like fusions, like HSI fusion with MSI, or we can do super resolution without MSI, just the HSI itself. Can we improve its spatial resolution just based on some software? So there are many interesting things going on in this area, but today I will only focus on classification. This is some processing chain. I copy this from a tutorial paper published in Signal Processing magazine. So we have original data come in, then we need to do some calibration or atmospheric correction. Then we got at surface reflectance data that if needed, dimensional reduction. Then this dimensional reduction could just based on the physical bands, or we can also do this in the feature space. We do projection. And then for the end user application, that could be unmixing, I just mentioned, it could be detection or classification, and so on. Okay, so I'm going to focus on representation-based classification. Because of deep learning techniques nowadays, if you read papers, most of people are talking about all different kinds of nets, deep learning nets. They are doing classification. However, their performance is highly dependent on the availability of large amount of training samples. But for remote sensing data, we may not have that amount of training samples. So particularly when we have this very high dimensionality data, then the requirement of training samples is also significantly increased. So here I'm not going to talk about any deep learning stuff. I will talk about some representation-based classification. This is something we have started several years ago. I think it is pretty interesting because this type of classification does not have the traditional training testing fashion. And it does not require large amount of training samples. So it's mainly just like we have a bunch of training samples, then we have a testing pixel. I want to know which class it belongs to. I just do regressional analysis using these training samples. Then those classes produce the minimum amount of error residual. Then we assign the pixel to that label. So that is a mainly idea. And then we can apply this constraint. We can apply sparseness constraint, or we can apply collaborative constraint. So in my research, I focus on collaborative constraint simply because it has a closed form solution and the performance is highly efficient. So this is the basic model. So we assume X is a data matrix, training sample data matrix containing all the samples, label samples. Then given a testing pixel Y, I want to know it belongs to which class. The objective is to find the weight W, weight vector W. So that is the original regressional analysis. But here we add a constraint, which is a norm 2 constraint. So without this Tikhonov matrix here, if we just do lambda W norm 2, the meaning is that because overall it's a minimization problem. So if this norm is very small, that means we allow all the training samples to contribute equally in the representation. So that means we encourage the collaboration between the training samples. And we know that there's another approach is to sparse representation, which means we want this W vector has many zero entries, as many as possible. That means training samples, they are compete each other. So if I represent this testing sample, I don't want another one to represent it. So there's the relationship is for competition. But here, if we do norm 2, that is a collaboration. And then here we introduce, here this is supposed to be lambda. So here we introduce this constraint matrix called Tikhonov matrix. So you can see this Y and this with each of the training samples, that's the Euclidean distance. If this Y is very similar to that training sample, this distance is very small. And if it is very different to that training sample, then the L2 norm is very large. So put 2 here, that means if that corresponding gamma is very large, because the training sample is very different to this testing sample, then that means the corresponding weight has to be small because it is different from the testing sample. So the W cannot be large. So in this way, we can control the difference of the training samples, not just simply say, hi, everybody have the equal chance to represent this Y. We do some gamma to control how much that actually can contribute to this collaboration. So, but anyway, if we because it's L2 norm, so we can just take derivative set to 0, then we can have a very nice closed form solution. Without this lambda, if lambda equal to 0, this is just a traditional regressional analysis, which is a pseudo inverse of X. But then we add this gamma, so this is we have a regularization term. Okay, after we compute this W, how to make the decision? So for the corresponding part of class, so let's say if we have 10 classes, for each class, we have the training sample set. Then we grab out the corresponding W to estimate this representation residual. So if we have 10 classes, we should have 10 residuals. And the one has a minimum residual, we assign the Y to that class. So you can see the overall procedure is very simple. The solution is just one line of command. We can easily generate the result. So here is some analysis, because the one I just mentioned is a basic version, but we can have different type of versions. For instance, the representation, when we do the representation, we can do pre-partition, which means we just do class-based. For each class, we find this representation rather than we put all classes samples together. Or we can do, as I mentioned, we can put everything together for representation, then we partition, post-partition, then find each class-specific residual. So we call it post-partitioning and pre-partitioning. And we can also improve this performance by using the kernel version. So which means the original version is linear, but we can extend it to a nonlinear version. So this is just some analysis. So we have NS, that is the original regressional analysis doing pre-partitioning. And the CRC, that is the corresponding version. But it is doing the post-partitioning. So you can see, as long as we can find a good parameter lambda, the performance, the highest performance are pretty similar. And then this is ERS and CRT, that is with this Tikhonov regularization. So NRS is the pre-partitioning and the CRT is a post. And the highest performance is very similar. However, if we do the kernel nonlinear version, then looks like the post-partitioning I just introduced will do a much better job than the pre-partitioning. I believe that's because when we do this nonlinear mapping to an even higher space, which can improve the class separability, we have to consider all the samples together rather than the class-specific samples. But anyway, that is original versions. So the one I'm going to show you for the experiments is that we have additional regularization. That's a spatial regularization. That's because when the sensor technology is improved, spatial resolution, particularly for airborne hyperspectral data, the spatial resolution is also increased. We can easily get like 2-3 meters per pixel. So if we can add the spatial information in many situations, it can also help to improve the classification performance. So the basic idea here is we still have the first two terms, but we add a third term. This is a gamma. Then we have S matrix multiplied W. So the S matrix, that denotes the Euclidean distance among the neighboring locations. So what that mean? So ACBC, we assume that is the spatial location of the testing sample, and AFBF, that is spatial location of the training sample. Then we calculate this spatial coordinate distance of the testing sample and to each of the training samples. So we got another set of Euclidean distance. So just like this gamma, that is about spectral similarity or locality, but this S is about the spatial distance, because here we assume if spatially very close, then that testing sample should be very similar to that training sample. Then we give this training sample a very high chance in the representation. So that's very similar idea. However, this term for the spatial regularization, it's really about the spatial local. And then this gamma, this term is in the feature space local. And these two, we tune this lambda and the gamma, so we let them to compete a little bit to see what is the best way to find the representation coefficients. So then the same thing is that we have this closed form solution. So the only additional calculation is to calculate this spatial distance. Okay, so I'm going to show you some experiment. So here we use the average sensor data. One is the Indian pines, another is Salinas. Both are about agricultural fields. For the Indian pines, after the bed band removal, we have 200 bands, and we have a corn and soybean tillage practice as classes. So we have corn not till or corn minimum till. And then we also have soybean not till or soybean minimum till. And for Salinas data, then its spatial resolution is 3.7 meters. And we have Falun, we have 3 classes used for classification. And in the experiment, we only choose 10 training samples for each class and the rest of samples for testing. And each classified runs 20 times, and we show the average performance. So we compare, so we have the CRT, SACRT. So this is original collaborative representation. This uses spatial regularization. This is SCRT is this is for sparse representation, and we have others like KNN, SVM, and so on. And this is running time to give us some idea how fast it is. So overall, you can see that for using the CRT, it is much faster than rest of approaches. So this just to give, because this is run in MATLAB and in a PC, but give us some idea how fast of CRT compared to the rest of the approaches. But when we apply this, when we add the spatial regularization, we have a little bit more computation, because we need to compute this spatial distance. Oh, I think I missed this one. We also calculate the overall classification accuracy for different classify. You can see that the if we use CRT, its performance pretty similar to SVM, but with CK means composite kernel. We use a 2 kernel, one spatial, one is for spatial, one spectral, one spatial. And these two are pretty similar. Compare the CRT to SVM, CK, and use a collaborative representation. The performance actually is better than the sparse collaboration. But after we add this spatial regularization, the performance is even more, it's significantly improved, in particular for the Indian pines, 2 Indian pines cases. And this one showed some classification map. You can see that without using our approach, other approaches has pretty strong misclassification. But this SACRT, the performance is pretty accurate. And this is another, this is about soybean. And then this is about Salinas data. And this data actually is simpler than the Indian pine approach. But you still can see some misapplication. The color difference here, but the SACRT, the performance is almost perfect. So this slide just summarize a little bit. Here we propose to use the spatial awareness CRT for agriculture tillage mapping. The reason I show you this as application simply just because this is the data that's available to us, and we have the ground truth available. And compared to other conventional classifiers, it offers the highest accuracy for tillage mapping. And then compared to its original version, adding the spatial regularization, it can also significantly improve the performance. And because it is very efficient, we believe it can be very promising if we want to use it for large scale data processing. So this is some quick discussion or introduction about some of my work. So is there any question?
Okay, thank you, Jenny, for your nice presentation. It seems SICRT, the collaborative representation with regularization, provides great difference with respect to other methods you compared, because the next method, support vector machine, provides approximately 28% in your example, while SICRT provides 96%. So it creates a new classification performance segment.